we are. Oh wow. Then we are ready to go. So it's a great pleasure to welcome virtually Abdallah Saffidine to Warwick. Abdallah is a lecturer at the University of New South Wales in Sydney, Australia. Abdallah has received a Discovery Early Career Researcher Award and previously a PhD from Paris-Dauphine. So I look forward to your talk.
Thank you very much for the introduction. Let me share my screen and my slides. So, well, thank you, first of all, Dimitri, for inviting me to give this talk to this audience. I'm very happy to present to you these results. So this is not yet a paper. This is ongoing work that I'm carrying with Andreas Herzig, but I'm very excited about it, and I wanted to share at the first occasion what we're doing. So in this work, what we are examining is a model logic called the dynamic logic of propositional assignments. This is a model logic that Andreas Herzig and colleagues came up with, I think in 2013, and it was following a long tradition of coming up with new logics, new model logics for the past 20 years, but I didn't really follow all of that. At some point, Andreas Herzig, gave me a challenge saying, okay, there's this thing that we don't quite know how to do. Could you help us with it? And I said, I can have a look. And there we started collaborating. So I joined this collaboration to help on the technical side, but I didn't have a very big logic background. I mean, beyond what typical computer scientists have. And so I don't know too much about the history of model logic and things like that. What I'm more used to thinking about is computational complexity of problems. And it was on the occasion of a complexity talk that Dimitri and I met for the first time. And as I was trying to solve on this challenge, I realized that this dynamic logic of propositional assignment fits really well with my perspective on complexity theory within the polynomial hierarchy. And I will try to give you some introduction to this logic and some of the results that we're developing. Just give me a second as I charge my laptop. All right, so what is happening today? Well, I'll start by introducing to you that DLPA, Dynamic Logic of Propositional Assignments. We'll think of it in terms of propositional logic and quantified Boolean formulas as a warm-up, and also to kind of illustrate the concept that we will use later on. After the warm-up, we'll talk the syntax and semantics of DLPA, and I will show you a few modeling that we can do with DLPA to kind of convince you that it's fairly expressive in an informal sense. In the second third of the talk, I will have a look at how can we make a case, or how can we try to make a case that a logic is better than another, or is more interesting than another. And typical ways of asking these questions are through the lenses of expressivity, complexity, and succinctness. And again, we'll first have a look at classical propositional logic just to get familiar with the notions in case some of us are not. And then we'll look closer into QBF and DLPA. Eventually, I'll come to the result that DLPA is not more succinct than QBF, which was a big disappointment to Andreas. He had introduced this logic and he thought, oh yeah, it's going to be so much better because it will be more succinct. And no, well, it's not. But still, even though it is not more succinct than QBF, I feel that it's more natural, and maybe you will you might be convinced of that with me. We'll see. In the third part of the talk, I'll come into talk about computational complexity and look at three types of problems for these sort of logics: the satisfiability problem, the validity problem, and the model checking problem. We'll have a quick look at them on propositional logic again, and then we'll talk more about QBF, the polynomial hierarchy, and how DLPA connects with all of that. So as you can see, I'm talking about DLPA a lot. That's not surprising. That's the topic of the talk. I'm also talking about QBF a lot. And why? That's because DLPA, as we shall see, is a problem that fits well in the complexity class PSPACE, and the traditional PSPACE-complete problem is the satisfiability of QBF formulas. And so that would always be our reference. Within logics, the first problem I think of in that class will be QBF, so that will be the point of comparison. So let's get us started. So the first thing I want to do is just set our vocabulary straight. So throughout the talk, I'll define some grammars or syntaxes. So this one is for propositional logic, where we say that a formula can be either an atomic proposition, where P will always be in that set of propositions, fixed. The negation of another formula, disjunction, conjunction, implication. And from there, we look at what is the meaning of a formula. After we know how to write one, what does a formula mean? And through that, for that we have to define semantics or interpretation. And the first step is to look at valuation or model. And that will be, we will see that as a subset of propositions, and will be those propositions that are assigned true. And we say that a model satisfies the formula if it makes the formula true in a way that we'll see in details later on. In that case, we might write that V satisfies the formula. And then what we call the semantics or the interpretation of a formula will be the set of all those models that satisfy the formula. So here I've got a very small example where our formula is A or, not B and C. And I'm asking for 4 different models, which of them satisfy the formula? This is propositional logic. I don't think I need to give a formal semantics for you to already know the answer to these questions because you've seen that before. So if my model is the singleton A, well, yes, my formula will be satisfied. If I assign A to true, that disjunction is satisfied already from the left-hand side. I don't have to think any further about it. If my model is B, in other words, I assign B to true and all the rest to false, then my formula is not satisfied. If I assign A and B and C to true, then my formula is satisfied through A. So these are examples of models, and some of them satisfy the formula, some of them do not. Okay, so that's the sort of language that I'm going to use to define DLPA, QBF as well. So let us start with QBF. So the grammar or the syntax for QBF, quantified Boolean formulas, will be quite similar to propositional logic, because we have the same constructors: atomic proposition, negation of a formula, disjunction, and then we also have this constructor where uppercase P is a finite set of atoms, and so we write there exists P phi, and that means there exists an assignment to the variables in P so as to make phi true. If we define the interpretations or the semantics formally, we get that the set of assignments that make the formula top true is everything. Any assignment makes the formula top true. If our formula is just an atom, P, then the interpretation are those valuations, those model where P is set to true in the model. Those are the one that make the formula P true. If we have the disjunction, we just take the union of the interpretation of the subformulas. If we've got the disjunction, we take the complement over that set. And then when we have that quantifier, there exists P phi. We will be looking at those valuations such that we can set some of the variables in P to true, some of them to false, or the rest of them to false, in a way as to satisfy phi. So we partition P into Q plus and Q minus. And from our valuation, our candidate valuation, if we remove those negated from it and we set the other ones to true, that should belong to the interpretation of the subformula. So let's have a look at an example. So our target formula is there exists A for all B. B is equivalent to C, or A is equivalent to D and B is equivalent to D. I haven't defined equivalent and for all in the syntax, but these are syntactic sugar that we could define additional. So let's have a look. What about the model C? So that means in this model, C is set to true, all the rest is set to false, in particular D is set to false. Okay. Does there exist an A such that for any value of B, B is equivalent to C, or A is equivalent to D and B is equivalent to D? The answer is yes. I can set the value of A to be false. Once the value of A is false, I can look at the value of B. Is the value B true, then this branch holds and my disjunction is fine. Otherwise, if B is false, so that's when I'm looking at removing the empty set, then, oh, sorry, that's the negation. Bear with me. For all is defined as the negation of the existential negation. So I need to check that for every partition, I would be fine. So if Q plus contains B, Q minus is the empty set. My subformula is true because B equivalent to C. And if my partition is Q plus is the empty set, Q minus is just B, then my formula will be true because A is indeed equivalent to D and B is indeed equivalent to D as well. And the other ones go through the same way. I want to highlight this third one and the fourth one. What's happening in the third one? We've got the model A, B, C. And here we have a quantifier over A. Well, that's not a problem according to the semantics here. We are just going to either erase A from the starting valuation or write over it. So as soon as a variable is quantified in a block like that, whether it was there before or not, is discarded, and only through the partition is the new value assigned to it decided. Okay, so syntax for quantified Boolean formulas and the semantics. As I was observing at the end, our quantified Boolean formulas do not necessarily need to be completely quantified. Like here, C and D, there's no quantifier next to them, and that will let us examine different models that give them some value, true or false. Okay, so now let's get started with the dynamic language of propositional assignment. So what's happening with this thing? With this thing, we have formulas, but we also have programs. So the grammar is quite more complicated. In the world of formulas, we still talk about atomic propositions, negation, disjunction as before, but you've got that new thing here, diamond, pi, phi, where pi is what we call a program. And programs are of different sorts. Some of them are assignments, some of them are tests. They can be the sequence of two programs. They can be the non-deterministic union of two programs. And they can be the iteration or the Pliny star of a program. And so from formulas can invoke programs in the diamond. And programs can invoke formulas in assignments and in tests. So there's that sort of back and forth between these two types of things. So what does it all mean? Well, I wrote a bit of intuition at the bottom of this slide that maybe can help us get started. So the first thing is that we will define a dual operator to the diamond pi phi called the box pi phi. Box pi phi is the dual as you would usually find a dual. Negation of the negation. Now the intuition behind diamond pi phi is there exists some execution of pi that will make phi true after we execute pi. And the dual is phi will be true after every execution of the program pi. So pi is a program that we're going to run. And after it has finished running, we evaluate the formula, the subformula. And you could see, at least with that non-deterministic choice between two subprograms, that the program could execute in different ways. And so the diamond will say, is there one way to execute it such that the formula holds? And boxes, would it hold after any execution? Okay, assignment tells us, so this is inside programs. Diamond and box were in the world of formulas. Now I'm inside the world of programs. So pi receive phi. It means, okay, I've got my current valuation, and I'm going to change the value of p in it. If my valuation doesn't contain p, maybe I will add p to it. If my valuation contains p, maybe I will leave it there, maybe I will remove it. To decide what I'm doing, I look at phi. I look, does phi hold in the current valuation? If so, I update p to be true if it wasn't already. If phi does not hold, I update p to be false. In other words, I remove it from my set if it was there. The test, I evaluate my formula, and if the formula is false, I fail. The program fails, like assertion error in C, or there's no outcome. And this sort of failure is especially relevant when we think of the diamond operator. Phi is true after some execution of some non-failing execution of phi. If an execution of pi fails, then we can't get to the end of it, so we can't make phi true. So we have to look for a different execution of pi that would not fail. So that's how we would use the test. Sequence, this one is very easy. We execute the first program, then we execute the second. Non-deterministic choice, we will execute one of them, not specified then which one. It's non-deterministically, one of them is executed. And depending on whether this thing is inside a diamond or inside a box, that would mean that after executing pi1 or after executing pi2, the subformula will hold. Or it means after executing pi1 and after executing pi2, the subformula would hold. Last but not least, the clean start tells us we're going to execute pi again and again and again, some number of times. And this is a non-deterministic choice between executing pi 0 times and the valuation does not change, executing it once and the valuation changes potentially, executing it twice, 3 times, etc. So some finite number of times pi is executed and then we proceed. So much for the intuition. Now let's go to a bit of formal definitions. First, one way of looking at programs is to see them as a relation on evaluations. So take evaluation V, a set of atoms, and we'll look at the program P receives phi, so an assignment. The evaluation V will be in relation with the evaluation V union P through the program P receives phi if phi holds is satisfied by the evaluation V. if phi does not hold, then v will be in a relation with v minus p. So that's how we update the evaluation. That's how we change it based on the evaluation of the formula. So we get these programs, and a relation on valuation tells us from the input valuation or from the left-hand side valuation, we can get into the right-hand side valuation by executing the program. So for the test, because the test won't do anything if it succeeds, we need the two valuations to be identical, to be in relation. Otherwise, they're not going to be related at all. And then to be related, the test needs to succeed. Otherwise, we can't go from V to anywhere. Sequential composition is like transitivity of this relation. I can go from V1 to V2 by executing pi1, and I can go from V2 to V3 by executing pi2. Non-deterministic composition, either I can go from V to V prime through pi1 or through pi2. And clean star is I've got some number, finite number n, such that if I can go from V to V prime within n step. And because we see these programs as relational evaluations, we can write the interpretation of a program to be set of pairs of evaluations, not those that are related. So now we're ready to define formally these interpretation for formulas. So nothing changes for atoms, negation, and disjunctions. That was the same as for QBF or propositional formulas. And now for the diamond, we'll say the semantics of diamond pi phi will be those valuations, those starting valuations, such that there's an ending valuation v prime that are related according to pi. And v prime has to satisfy the formula. So is there a v prime that I can reach by executing pi and my v prime satisfies my formula? If so, then my v was satisfying the diamond. And similarly, we can define formally the relation for programs as follows. So for the assignment, it will be those valuations related to themselves plus p when they satisfy phi, and them related with themselves minus p when they don't satisfy phi. I'm saying the same thing in 3 different ways because I want you to really understand these foundations. But yeah, it's the same look as we had on the previous slide. The test, as you can see, there won't ever be any change as we do the test. Either the pair is not in the interpretation or not, or it's the same on the left and on the right. Sequence is the composition, and non-deterministic choice is the union of the relations. Okay, so let's go through an example together. And I've put as a reminder my intuitive understanding of these programs and of that model operator, diamond pi phi. So, okay, ignore this part. I look at 3 formulas, and I want to know if these models satisfy the formula. So let us first look at the formula. Diamond A receives not A, union B receives B or A. So that's our program. Is there a way of executing this program such that by the time we're done, not A and B? So if I start from the empty set, in other words, A is false, B is false. Okay, if I go for the left subprograms, it will make A true, and that will fail my formula. So I have to go for the other one. B receives B or A, but I'm starting with nothing, so B receives false, and that also fails my formula. So the input valuation empty, everything is false. does not make diamond, blah, 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 not A and B true. If I start with A, okay, if I go on the left, that makes A false, which is a good start. But B remains false, and I need it to be true, so that doesn't work. And if I start from A and go to the right-hand side, then A will remain true, and so my formula will also not be satisfied. What about B? Well, B, so I start with B is true and A is false. I can go through the second branch of the non-deterministic choice. So there exists a way where I'm assigning B receives B or A, B receives true or false, so it receives true. A remains false, and that means that not A and B holds. And so B alone is a model of this DLPA formula. Now A comma B, so A starts true, B starts true. I can go through the left branch, make A false, and now A is false and B remains true. So much for the non-deterministic choice. Now we've got almost the same thing, but a sequence. A will toggle, and after A has toggled, I will do something about B. I will update it. So if I start, let's say I start with A is false. I toggle, I start with A is true. Apologies. Then I toggle it. Now A is false, and I try to update B. It remains false, so my formula doesn't hold. If I start with both A and B are true, I toggle A. Now A is false. B receives true or false, so B receives true, and not A and B is true. I like the last one because it has the clean star, which is always fun to work with. So this one is, we're going to do this: A receives B, B receives B or A receives not A, B receives B or A. We're going to do that any number of times. We can do it 0 times, 1 time, how many times we wish, so as to make the subformula true. So if we start from nothing, we toggle A. Now A is true. I update B with A true. Now B is true. So I've got, after the first time I do it, I've got A true, B true, which is not quite going to work. But I can choose to execute it again. I toggle A. Now A is false. B receives true or false, so it remains true. And now I can decide to stop iterating. A is false, B is true. And so my subformula is satisfied. So if I start from the empty model, I can choose to execute the program twice, and that'll be good. If I start with A, starts true, then I toggle it. Now it's false. Then, okay, B remains false. I execute it a second time. Now A is true. B becomes true. Now A is false. B remains true. And I exit and I satisfy my formula. And so on and so forth. So it turns out that this specific DLPA formula with the clean star will, any model satisfies it. These 4 in particular. Okay. Of course, please feel free to interrupt me. I'm happy to answer questions at the end of the talk and in the middle as well. Okay. So we've built some intuition. What can we do with DLPA? So I want to try and show you that many things that you would do in normal programming, you can do that in DLPA, which justifies calling these things programs. So first syntactic sugar I'll define is skip. Skip means don't do anything. It's like a placeholder program. So this one we can define as being test of top. So any evaluation satisfies top, and so then it's going to be connected to the next evaluation, which will be identical to itself. So skip does nothing. Fail, well, there is no evaluation that would satisfy bottom, and so any evaluation would fail and be not connected to anything through this program. if then else. Given a formula and two subprograms, what could we do? Well, we can do test of phi, then execute pi1. Choice, test of not phi, execute pi2. And so I find it very interesting because this is a very deterministic construct, which we expressed through non-determinism. So, yeah, my input valuation, I'm going to look at, well, I choose either of these two, but I need to choose a non-failing one. And of course, exactly one of them will be non-failing. The other one will be failing. One of these two will not, the input valuation will not satisfy the test. And what happens afterwards is going to be the subprogram. The while loop, as long as my formula holds, I can do my program. And then if it still holds, I continue to do my program. So I do the test, and if it holds, I can execute more and more. Now, I need to make sure that I don't leave too early, that I don't choose to not execute the program at all, for instance, or to only execute it once, even though the formula would remain true. And that's why at the end, I need to have the test that the formula is false. And if you think of Hoare triples or precondition postconditions in programming, then when I'm executing the body of my loop, I have as a precondition that my condition holds. And by the time I finish the executing while loop, my postcondition is that the formula does not hold anymore. So this is very reminiscent of what happens in the semantics of programming languages. We can define the repeat until in a similar way, but I spare you. Here is another example. We can define counting, or counting up to 2 to the power n by selecting specific propositions, let's call them P1 to Pn, that will encode a binary number, an n-digit binary number. And then if an assignment to P1 to Pn represents a number, how do we update the assignment such that the next values they have correspond to the next integer in line? Well, it can be done by just executing this sequence. And let's assume that you trust me on this. Won't go into the details, but yeah, we can, if we execute these n steps, these n assignments, what will happen is that at the end of the execution, the interpretation of the values of our propositions as binary will be 1 plus the interpretation that we would have had before. Okay, so that's it for my introduction to DLPA. Still happy to take questions, but I can now tell you about comparing logics. So
Abdallah, just to let you know, we are about slightly past the middle of the slide, just to let you know.
Sounds good. Thank you. Yep. We will not spend the same amount of time in each section. All right. So when you want to compare logics, let's take propositional logics and CNF, conjunctive normal form, which I defined later confusingly. Sorry about that. Let me go to the definition of conjunctive normal form. There it is. So my conjunctive normal form is either a proposition, the negation of a proposition, or a disjunction. These define my clauses. And my formulas, they will be conjunction of clauses. Okay. So if I want to compare conjunctive normal forms to arbitrary propositional logic formulas, what can I say? Well, I can say, well, they're kind of a subset. So anything that's true about them will be true about the other ones. But maybe the propositional logic ones are more because the grammar is a bit bigger. Well, it turns out that propositional logic is not more expressive than CNF. And here I'm also defining what more expressive means, of no more expressive. There exists a transformation that goes from propositional formulas into CNF, such that the interpretation of the input formula is the same as the interpretation of the output formula. So any model of one will be a model of the other and vice versa. How can we prove it? Well, the transformation can be just applying De Morgan's laws and distributivity. At the bottom, I'm considering an example phi n, which will be x1 and x and y1, or x2 and y2, etc. If I apply De Morgan's laws and distributivity to this formula that is not in CNF, I obtain this formula that is in CNF and corresponds exactly to it. It has the same models. So propositional logic is not more expressive in CNF. Similarly, the satisfiability problem of propositional logic is no more complex than the satisfiability of CNF. Why? Well, there exists a transformation of polynomial size from prop to CNF such that my input formula is satisfiable if and only if the output formula is satisfiable. For instance, the Saffidine transformation does that. We can get there by introducing, again, I'm starting with that phi n formula. I introduce auxiliary variables that will correspond to these sort of constructs. And that T of phi n will admit a model that satisfies it if and only if the input formula did. But we can say that propositional logic is strictly more succinct than CNF. And what does that mean? It means that there exists no polynomial size transformation from propositional logic to CNF that preserves the models. So you see, with expressive, we want to preserve the models. With complex, we want to preserve satisfiability only and have polynomial transformation. And with succinctness, we want to preserve the models and have polynomial guarantees. And as a matter of fact, prop is more succinct than CNF. So this question about expressive, complex, and succinct are the ones I'm going to ask about DLPA and other logics, especially QBF. So I want to compare DLPA and QBF. First, going from QBF to DLPA, I can show that QBF is no more succinct than DLPA. DLPA is at least as succinct as QBF, and I will tell you that on the next slide. And then expressive and complex, they're just the consequences of this fact. Now going from DLPA to QBF, for any DLPA formula, I can construct a QBF formula that will be having the same models. And in 2013, a transformation was given that takes exponential size. DLPA satisfiability in DLPA is no more complex than in QBF, and that was obtained in 2014 by giving a PSPACE algorithm to solve it, basically. And so we know that there is a transformation via that PSPACE algorithm from DLPA set to Turing machines, and because QBF is hard, from Turing machine to QBF. And so that gives us a transformation that preserves satisfiability of formulas. And the new result is that DLPA is not more succinct than QBF. So we exhibit the transformation into a polynomially sized QBF that has exactly the same models. So as promised, QBF is no more succinct than DLPA. How do we show that? Well, we give that transformation S that maps atoms to atoms, disjunction to the transformation of the disjuncts, negation as well. And for the quantifiers, that's the non-trivial one, what do we do? Well, for every atom, let's say that our set is P1 through Pn, I will say, I choose non-deterministically to set P1 to true or to false. And then I choose to set P2 to true or to false, etc. And then I put all of that in a diamond. Was there a way to set all of them so as to satisfy my transforms and formula? And that's it. If we apply it to this example formula, there exists an A such that for all B stuff, Well, I can have diamond of A receives top or A receives bottom, and then box, the universal B receives top or B receives bottom. So that means for any way of interpreting, of executing this, the sub formula will hold. And this transformation is, well, it's only a linear factor. So we can conclude that QBF is no more succinct than DLPA. In the other direction, it's a bit more complicated. A first idea is to look at these assignments and to say, okay, I want to transform, let's say, P receives top phi. I could introduce a new variable P and say P and T of phi. So now I'm forcing P to be true. And through that exists P, I forget what the previous value of P was. Similarly, if P receives bottom, I will force P to be false, and my exist quantifier will kind of choose it appropriately and erase its previous value. If I want to generalize this slightly, and I say P receives some formula phi in a diamond phi prime, I need to introduce a new variable. Let's call it P prime. And I will say that P prime has to be of the same value as the interpretation of that, as the evaluation of that formula. And then in my subformula phi prime, I will replace P prime with P. I think I got it in the other order, sorry about that. So I create that new variable, and then I plug it in the subformula. And that way, the old value of P here and the new value will not interact or will not mess one another. And similarly, if I've got a sequence P receive phi, then P receive phi prime, I introduce a first copy, then a second copy, and I modify my subformula accordingly. So that's the main idea. What this doesn't tell us is how we're going to deal with the clean star. And this is not a formal transformation anyway. So let's try to do things a bit more formal. So the main idea for our transformation is to define a function f that will tell us f of phi v means phi is true at some valuation v. And we will give valuation names like integers. As we encounter them, we have a global counter that increases step by step. So if I just look at the atom P and the name of evaluation V, then I can look at P indexed by V. So that's going to be a specific atomic proposition, P power V, or not P exponent V. Not quite the same as P, but it corresponds to it in the evaluation V. And we define recursively this transformation. So atoms I've described, negation is direct, same as disjunction. And then for the diamond, we will have, is there another evaluation W that I can reach? So I want to evaluate my formula on V. Is there a W that I could go from? I can go from V to W according to pi, and my formula phi will be true on W. And we have to define this. The G that tells us I can, from V, I can go to W following program pi. Well, this we could do. So let's say that we look at assignment. Can I go from V to W by assigning P phi? Well, I look at P, the atom PW, and it has to correspond to the F. That's the same as what we had before. And then I will make the relation between the other atoms to force them not to change between W and V. So I've got all these copies of atoms in my input formulas. I've got the V copies, the W copies, and I force them to be having the same value here. And that's the way to simulate time passing in the static world of QBF, by creating a copy and then saying either it's the same or it's updated. Okay, the test, this one is easy, I can skip. The sequence is there an intermediate valuation U such that I can go from V to U and I can go from U to W? So I introduce a new name, a new proposition accordingly. And then the non-deterministic choice is just a disjunction. But we still have to deal with the star. So, well, what's the star? The star, we can see that as I do nothing, or I execute pi once, or twice, or n times, or more. It's not hard to show that I don't need to go super high here. I can limit myself as 2 to the power, the number of variables that occur in my program. There's no point executing any more than that, so I can make that a finite sequence. And with some algebra, I can show that this is the same as executing the program, choose between doing nothing or you do pi, 2 to the power number of variables times. So by this point, we can reuse our definition of G for sequence and G for the union, and that will give us the transformation. Okay, that's going to work for expressivity. It's not going to work for succinctness because 2 to the power number of variables is too large. So how can we define that G for the star in a non-explosive way? And here we use a trick that is quite old by now, of Savage initially, and that you can find in Chandra and all the alternation paper. But I always get it from the Sipster textbook because it's easier, it's more modern. Essentially, we're going to define an auxiliary function, h, that will treat specifically that star. And h, VW pi n, stands for, we can go from V to W via executing pi exactly 2 to the power n times. And so we'll just set n to be the number of atoms. And this h can be defined rather easily. If n is equal to 0, so we want to execute exactly one step, so we call g on pi. If we want to execute n plus one step, we say, well, is there a middle point? I could go from v to the middle point, executing pi 2 to the n times, and then from the middle point to the nw, 2 to the n, and that will make 2 to the n plus 1 total. Okay, I'm still exploding here, but comes the trick of taking advantage of the universal quantifier. So I'll use a universal quantifier x so as not to repeat the recursive call to h. And so I say, okay, I've got a starting valuation and an ending valuation, v1 and vw and w, v1 and w1, and I'm going to test h on v1 and w1. And through that x, I will set the values of v1 and w1 appropriately. So if x is true, I'm checking the left one. If x is false, I'm checking the right one. And that way, a single recursive call through that universal quantification gives us the two tests. And now we don't have an explosive definition anymore. And so overall, we have a transformation that is quadratic in the length of the input formula. And the models will be the same. The interpretation of the input formula is the same as the interpretation of the output formula. And so that tells us that for any DLPA formula, there's an equivalent QBF formula of polynomial length, which was a bit of a surprise to us. All right. Let me conclude with some complexity notes. So I'll be interested in 3 decision problems. The satisfiability. Input is a formula, and the question is there any model for it? Is the interpretation not the empty set? The validity, given a formula, is its interpretation everything. So any model is a model of the formula. Any model satisfies it. And then the model checking, where now I'm given the valuation as input along with the formula, and I'm asked, is that specific valuation a model for it? If I look at these 3 questions on propositional logic or CNF or DNF, the complexity of these problems are NP-complete, co-NP-complete, or polynomial time solvable. For CNF, the validity is actually very easy, same as DNF, the satisfiability is very easy. It's only the satisfiability for CNF that's difficult. So these notions of satisfiability, validity, model checking, I'll ask on DLPA and QBF. And that brings me to the polynomial hierarchy that you may have seen before, where I'm organizing my complexity classes together. I've mentioned P, NP, co-NP already. PSPACE, well, that's the class of problems that can be recognized with a Turing machine in polynomial space, but it's also the class of that corresponds to model checking in QBF. And as we know now, in DLPA as well. But I like all of these intermediate classes as well. And one way of defining them is by saying, oh, I get a Turing machine and I give it oracles. So my Turing machine is especially powerful because on top of its normal course of operation, it can call in a special thing that will be more or less powerful, and we put it on as an exponent. And we get all of these classes by choosing appropriately the opponent and the exponent and the base power of our Turing machine. Well, I find all of that very complicated. I don't like oracles. And I like that we can see all of that through logic as well. And maybe that will make some sense to you. Let's have a look at that. So I want to define a measure of depth for my formulas. And that's the alternation depth. How many quantifier alternation? So if I'm looking at QBF formulas, I will increase my depth by 1 whenever I've got existential quantifiers. If I'm looking at DLPA formulas, I increase the depth by 1 whenever I've got a diamond. And this is not surprising because I can simulate the exist with the diamond. And otherwise, I just take the max of the 2 choices if there's 2 choices. The star, I say it has infinite depth. Okay, so at this point, I'm capable of saying for every formula, what is its quantifier alternation depth, or the model depth. And there comes this alternative characterization of this polynomial hierarchy, is that if I look at QBF formulas of bounded depth I, then the satisfiability problem is sigma I plus 1 p complete, and the validity problem is pi I plus 1 p complete. And same thing with the DLPA through the corresponding depth measurement. Something funny happens for the model checking problem, that we don't get quite the same thing, and this is something that I like, but yeah, I want to say a few words about that. So what is this class delta p I plus 1 complete? If we look here again, it's here in the middle and here as well. So delta p I plus 1 is, I have a polynomially powerful machine, and I've got a sigma IP oracle. Now, I can be in the column of satisfiability, in the column of validity, or in the column of model checking. But when I do model checking for QBF, I only get this theta. The delta, I don't get. And if you want to get access to these delta classes through QBF, you have to ask a very unnatural question, in my opinion, which is not the satisfiability, not the model checking, and not the validity problem, is the following. So I give you a QBF formula, and I say, so I've got the list of propositions that occur in it. Now I look at all the models of my formula, and I sort them according to the propositions that occur in my formula, and lexicographically. So I'll give an order on my atoms, P1, P2, Pn. And now, among all of the models sorted, I look at the last one, and then I look at the last atom in there. Is it true or false? And that's what makes it a yes instance or a no instance. This is horrible. I don't want to use that when I'm reducing delta something problems. But with DLPA, it's much more natural because just the model checking problem for DLPA at the appropriate depth. I've got one last one here. It's DLPA with simple assignments, and this is the variant where the assignment of DLPA, let me go back to the grammar. This is where the assignment will only be P receives true or P receives false. If that was what I started with, instead of arbitrary formulas, then I will get I'll get theta I plus 1p. So I can get access to all the core elements of the polynomial hierarchy, choosing appropriately my my syntactic fragment. And I think I will wrap up here in the interest of everyone's time. So I think that DLPA is a very good language for the PSPACE class. It's as succinct as QBF and other ones, but I think it captures very naturally the variety of PSPACE. I've made a case with delta IP that can be captured through the model checking problem, but even if you think of other types of PSPACE problem, like planning, or I run a Turing machine in polynomial space. If I want to encode that problem in QBF, it's complicated. I need to use tricks that Savage came up with in the 80s. In DLPA, it's very easy. I just make the choice and then a star. Repeat the action, the choice of action again and again and again until you get to an accepting state. And this is like 3 lines, whereas in QBF, it will be much more complicated. So if I want to encode, say, planning problems, it's easy in DLPA. And that's one source of complexity for PSPACE is, oh, I've got a very long horizon and I need to do some choices, and I can't do that in polynomial time, but I'm not going to create something new, so polynomial space is enough. Or I can have these games like generalized tic-tac-toe or hex. They're also PSPACE-complete, and they're complete not because of the depth, but because of the alternation between existential and universal players. And I can get that very easily in DLPA as well, with the box and the diamond. And so I think, yeah, it captures the variety of PSPACE. And as I was telling you, we can get all of this syntactic fragment of DLPA that will correspond to polynomial hierarchy problem classes. Now, what's next? With some students, and also by myself, I'm trying to test that hypothesis, like going beyond theory. And to do that, I have some students where the task for them is to write domains in DLPA. So they take planning problems and they create the DLPA corresponding formula. Some of them take games and they create the DLPA corresponding formula. And that will help us assess if it really is a convenient language to write things in. I've got another student writing on how to create a solver, like a piece of software that can solve the model checking problem or the satisfiability problem. We could do that by reducing to QBF and calling off-the-shelf QBF solver, or we could create a direct DLPA-specific piece of software. And finally, grounding. This is not an issue that I want to say too much about, but when you write a lot of the same thing, it gets tiresome. And so you want to have a slightly higher level language that can reduce to DLPS such that it's more concise. For instance, if I tell you, what is the impact of putting a piece in tic-tac-toe in some location? Well, then there's a piece in that location. This is not actually DLPA or QBF. This is, I said, some location. And some location is a meta variable. And so grounding is a way to do all of that in a clean way. And I want to spend a bit of time thinking of the grounding for DLPA. Thank you all for your attention and your patience. And yeah, if there's any question, I'm very happy to look into this.
So let's clap. Thank you very much, Abdallah, for the very nice talk. So are there any questions? So maybe I could ask a very brief question, if that's okay. So you mentioned the direct solving approach to for your logic. So QBF is somehow encoding problems in QBF can be a bit hairy, as you, I think, know much better than I. So I'd assume that if you encode problems in QBF, you need to employ kind of a range of, well, shall I say, programming idioms. And if you encode instead in DLPA, you'd be able to say this more nicely, but then the solver would need to somehow be able to deal with these idioms directly. So do you think that this could be an advantage of DLPA over QBF that is possible to exploit in an actual tool?
Yeah, that's a very good question. And I've been thinking about that for a while. So QBF is much more restricted, like not in theory, but in practice. It makes some tasks easier for the solver in that it can do a very elaborate thing, like all this close learning that I have no idea how we would get there in DLPA. Learning new things that were not there in the formula just by observing and making some of inferences like that. And that helps it a lot. But on the other hand, because encoding in QBF is a bit cumbersome, that also adds an overhead that we don't get in DLPA. And so it's not that the solver would have to recreate these adjunts itself. I don't think so. Like imagine I want to encode tic-tac-toe. So I've got to choose where to place among 9. One way to do it in QBF is to have one propositional variable that corresponds to each of the location for the first 9 step, and it will be true if I choose to play there. But then I need to encode that I'm not going to play at 2 different spots at the same time, and that I'm not playing at 0 spots. And still, I have 9 variables. So the choice that the solver has to go through is 2 to the power 9. But in DLPA, I would just have the non-deterministic choice between the program play here and the program play there and the program play here, because these are choices not between 2 Boolean values for one variable, but choices between sub-programs that will each have like its own effect, like making a move. I can have a choice between 9 directly accessible to the solver. And so inside the solver, when it explores the game tree, there will be a branching factor of 9 instead of a branching factor of 2 to the power 9, or 16 if you do very tricky encodings. So yeah, I think DLPA would make it harder to do very advanced things like close learning, but it will also make it not so hard for the solver to be good because there are not so many choices to begin with. Because the space that you will be working in is so much closer to the domain space. Whereas in QBF, you have all of these extra propositional variables that you have to be there to get the consistency, but it just merges the water.
Well, thanks very much. Yeah.
Which one of the two will be the more significant factor? That, well, we'll see next year.
All right. Well, fingers crossed. So, all right. So, I suppose if there are any further questions, colleagues could, and everyone could just pass them to myself, and I'll pass them to you, Abdallah, or they can contact you directly. So thanks very much again for joining our seminar.
Yeah, thank you for having me.
Thanks a lot for coming. And yeah, I suppose it's what's actually the time in Sydney? It's quite late, probably.
It's 10 past midnight.
Oh dear. So so it's kind of time to say Happy New Day. I see.
Well,
all right.
Have a good afternoon, all of you.
Well,
good night.
Good night. Thanks very much, Abdallah.
Bye-bye.
Take care.